Okay. Tom, good. May I start? Okay. All right. Well, last week we talked about single cycle processor. The general idea is I want to make sure that you understand how we construct data part in the processor. So we have learned about the data part. We have learned about the control signal. And we basically ignore the control unit because you do not have strong background in finite state machine, but never mind. Okay. So today we're going to improve our processor from last week. We try to make it faster in a sense, but how? There are several ways. Let's start with first idea. We will convert from single cycle to multiple cycle. And let's see why it might be faster. Okay. All right. First of all, we have to understand why single cycle is a bad idea. If you remember last few slides from last week, we talked about one thing that we call the critical part. Okay, can anybody remind me what is critical part? จำได้ไหม critical part คืออะไร The slowest instruction, right? The slowest operation that you have to pass to most components, and that's the thing that tell you how fast can our clock be นะฮะจำได้ใช่ไหมฮะผมบอกคำนวณ critical path คุณได้เลขหนึ่งเลขแล้วเลขนี้ก็คือห้ามใส่คล็อกที่เร็วกว่านี้ That's the idea from last week, the last few slides. We do the critical part and then we come up with some cycle. But the truth is, some instruction that give you the critical part, maybe it's just one or two instruction, right? That really slow, But other instructions, maybe finish early. But with our design, we say we want only one cycle per instruction. That means we have to select the longest time, the slowest one. That means this is the potential that we can maybe start new instruction, but we cannot, because by design, we have to make sure that one cycle we can finish everything. So we don't like single cycle processor. It's slow. It's slow because it have to wait for the slowest instruction. There are more to that, like memory. When you have to read or write from the memory. Well, basically read, not write. Memory is not that fast. Let me give you real examples. Your current processor, likely it's gonna run at maybe let's go back a little bit, 4 nanoseconds per cycle. 4 nanoseconds per cycle. But memory, the fastest memory, maybe still at 100 nanoseconds per cycle. So that means whenever you have to read or write from the memory, slow. So that means if you load, you have to wait. Okay. So that's bad idea anyway. So can we make it better? Can we make it better? Let's try to understand memory a little bit. Well, there are several kinds of memory. Maybe you have heard of it. Static memory and dynamic memory. Ever heard of it? Dynamic device เคยได้ยินไหมฮะ Dynamic memory DRAM เคยได้ยินว่า DRAM SRAM static รู้ไหม SRAM กับ DRAM Anyway dynamic memory is just a bunch of capacitors two wires and capacitors and this is the real pictures it's physics in a sense larger memory gonna be slow the more memory you have it's gonna be slow all right pretty straightforward it's like we have small box and big room you want to find something in a small box or in a big room which one would be faster small box of course so smaller is better smaller is faster นะฮะกฎฟิสิกส์ธรรมดาเลยอ่ะก็คุณมีปากกาหนึ่งด้ามมีกล่องใส่ปากกาหาปากกาในกล่องก็ต้องง่ายกว่าหาปากกาในห้องไม่รู้หล่นอยู่ตรงไหนนะครับ like that for the memory So we're gonna come back and see how can we make the memory faster later but for now in general large memory means slow okay and again later we're gonna make it faster with something that we call cache but not now that's later after the midterm we're gonna revisit the concept of cache okay so let's assume that somehow we can make the memory fast for now then what can we do to the processor to make it faster idea is simple maybe we can finish something earlier and start a new one finish early and start a new instruction right away but still the processor operate on clock at least that's the current technology for today processor operate with clock new clock come we have new state so the idea is maybe we can make one instruction use multiple clock in the sense that some instruction may use fewer cycles some instruction may use more cycles but we gain benefit that some that use less cycle we can start new instruction right away when we finish ขออนุญาตถามตรงๆถ้าบอกว่า flip flop เนี่ยต้องอธิบายกันเยอะนะรู้จักไหมรู้จัก flip flop โอเค flip flop คืออะไร flip flop คืออะไรบางอย่างมีสวิตช์คืออะไรโอเคไม่ต้องรู้ก็ได้let's say we have register in general register is like this you have a box you have data in you have data out and you have clock Whenever we have a new clock, we load new data. Okay, keep it simple like that. Okay. So the idea is, let's say you have somewhat complex logics. Let me try drawing this. Okay. I draw something like S equal C plus A B. Okay. เขียนอย่างนี้งงไหมไม่งงไหม Okay. All right. If we have flip-flop that would store the result, that means your clock gonna be like this. Make sure that you can finish everything within one clock cycle. But now I say I want to make this 2 clock like this. That means I have to remember something in between. งงไหมก็พูดง่ายๆผมเขียนประโยค s เท่ากับ c บวก a คูณ b ถูกไหมครับ if I want to make this 2 clock that means the first clock I would have to do something like d equal a b then the second clock I make something like this 1 clock each so I have to remember something in between just standard math like that but for circuit when you want to remember something you have to put in flip-flop or register so we have to add some storage element or register in between that way we can remember intermediate result and use it later เอาเชิญทันไหมฮะผมพยายามใจเย็นๆช้าๆให้คุณเข้าใจถ้าอันไหนงงจริงๆอยากได้ภาษาไทยก็บอกแล้วกันอันนี้ผมแอบมีประสบการณ์ไม่ดีกับการสอนเด็กอินเตอร์ไม่ใช่ที่เรานะที่อื่นที่มหาลัยอื่นเคยไปสอนมหาลัยอื่นหลักสูตรอินเตอร์นี่แหละคิดว่าโอ้แล้วก็สอนเบสิกมากเลยโปรแกรมมิ่งพื้นฐานอะไรเงี้ยตอนนั้น20 กว่าปีที่แล้วผมก็วาดรูปสี่เหลี่ยมมุมฉากหน้ากระดานแล้วบอกมาเขียนโปรแกรมหาพื้นที่สามเหลี่ยมกันสามเหลี่ยมใส่สี่เหลี่ยมมุมฉากอะไรเงี้ยก็อธิบายไปเรื่อยๆจบคราวก็มีนักศึกษาคนหนึ่งของมหาลัยนั้นเดินมาถามผมอาจารย์ครับที่อาจารย์ยกตัวอย่างแล้วอาจารย์พูดว่า right triangle right triangle คืออะไรผมก็อ้าวแล้วกูพูดมา2 ชั่วโมงนี่ไม่ถามกูอะไรเงี้ยคือผมโมโหมากเลยตอนนั้นนะครับที่พูดมา2 ชั่วโมงยังไม่รู้แล้วทำไมไม่ถามวะแล้วมารอถามหมดค่าว่า right triangle คืออะไรนะครับผมก็มุมหนึ่งก็คือไม่ได้อยากให้ภาษาเป็นอุปสรรคกับการเรียนอันนี้ก็พูดตรงๆแต่ว่าโดยหลักสูตรคุณเป็นหลักสูตรอินเตอร์แล้วเขาอยากให้สอนเป็นภาษาอังกฤษคือมันไม่ใช่ปัญหาผมสอนภาษาอังกฤษมันปัญหาคุณหรือเปล่าถ้าคุณเรียนไม่รู้เรื่องอะไรเงี้ยหมายถึงบางคำมันเป็นคำเบสิกมากเลยไงแล้วคุณไม่รู้ว่าเราจะให้ผมทำยังไงอย่างเงี้ยถ้าสังเกตผมพยายามไม่ใช้คำพิสดารอะไรเงี้ยนะซัมก็ซัมไม่ใช้ consolidate อะไรเงี้ยต้องมาแปล consolidate ให้ฟังอีกปวดหัวอืม นะครับอันนั้นถ้าตรงๆก็คือคุยกันตรงๆไม่รู้ถามอยากให้อธิบายภาษาไทยบอกคำไหนไม่ไหวบอกนะครับโอเค we good all right so now we have to add some storage because now you kind of cut the circuit cut the logic in the middle is like this I have to cut something in the middle that means I have to remember intermediate result and use it later so if our processor is like this actually I just draw the same pictures. That means you have to remember partial result and use it later. We call this intermediate resistance, or some books may call it shadow register. Whatever it is. Something that would remember intermediate result. So the idea is, if we can add intermediate registers in between, that means we can change from one big clock like this into two small clocks, and it just works. And we got a potential that if some instruction we only need an X, that means we can start new instruction right away in the next clock, rather than wait for another adder to do the S for us, like that. Okay, so we're going to do the same idea for our processor. Add some intermediate registers in the middle and change to multiple cycle clock. All right, let's try. If this is the standard data part of our processor, draw in a way that make it easy to understand คือขี้เกียจวาดรูป data part ใหญ่ๆปวดหัวมันอยู่หน้าถัดไปแหละนะครับ keep it simple first. Okay. So by design, this is actually about the same amount of time. So maybe we can have 5 standard cycles. ทำไมคนดูหน้าเปลี่ยนไปวันนี้ไม่ทำอะไรมันทำอะไรมาวะออกตัดผม Okay, so for our single processor, maybe we can just do 5 cycles right away. And what do we add? For the first cycle, you add instruction register. For the second, For the second cycle, we got the result from A and B, and then we feed A and B to this. Another cycle, we can add S. Okay, and this one we can add data like that. Okay, again, add intermediate register to remember intermediate result and use it later as an input for the next cycle. Okay, so for our design, wow, it's just pretty nice 5 cycles by design. First cycle, we add instruction register to remember the instruction that we got from the memory. Second cycle, you ask the register files to do whatever you want, then you got what? Basically two operand A and B. All right. Next cycle, we ask the ALU to do something, so we got the sum, the S. All right. Pretty straightforward. So if you draw the data part, it can be complex like this anyway. The simplified version. Okay. But let's see if we change from single cycle, single long cycle to multiple small cycles. Does it really make our CPU faster? Okay, let's do some calculation, see if it's really faster. So again, we come back to our equation, CPU time equals IC time CPI TC. Okay, I got some numbers up here. Okay, let's start with the single cycle. Maybe I use screen, right? Oh, you didn't ask any of you colorblind? มีใครบางคนตาบอดสีไหม I was I mean some student most people with colorblind they're gonna blind with red. If you see this as red, you good. This is blue. If you see the difference, you okay. But I there was a case that student colorblind red and I keep drawing and they confused. Sorry. If not, okay, I continue with I avoid red anyway. All right. Okay. I try green and blue then. Okay, let's start with single cycle. Single cycle processor. Single cycle processor. Okay, SP for short. This case, CPU time gonna be what? IC time CPI for single cycle that would be 1, right? And it say the original single cycle is 210 nanoseconds. Okay. Nanoseconds. All right. And we convert that to multiple cycle, and that's gonna change that from 210 to 45. So for multiple cycle processor, we would get what? CPU times equal, it's same program, same instruction set, so same IC. All right. And this is gonna be what? 45. So it's up to the CPI. If you can vary the CPI, and potentially it would be faster because on average this will less than 5, right? Right? Because the longest instruction would take 5 cycles, but we know that some instruction would take 3, some instruction would take 4. So on average, it's less than 5. That means eventually this would be faster. Right? Just plug in some numbers that less than 5, you win. But of course, the question asks for what potential speed up, right? So you have to do speed up equal like this and divide them here. Oh, by the way, I got a lunch meeting today. That means let's have no break in the middle and we finish a little bit early because I have to run for the meeting. Okay. All right. So we add few intermediate registers, and now we can use multiple cycles for an instructions. Some instruction that you just put S right back here, it would take what? 3 cycles, right? Some instruction that you have to read from the memory and write back, that would take 5 cycles. right? Some instruction that you only write to the memory and done, that would take 4 cycles. So our CPI gonna vary between 3, 4, and 5, depends on the instructions now. So by design, we add few more register, few more intermediate registers. Now we can have faster clock. Faster, I mean smaller clocks. But some instruction would use few cycles, some instruction would use small. On average, it's faster. Because now not every instruction have to wait that long. Okay, we good? So let's try to design our processor again, but now with multiple cycles. Okay. Let's try the OR instruction. What does it do again? RRS, or with the zero extent immediate, put the result back to RRT. But since now we have multiple cycles, you have to explain it as a cycle. We call this one logical RTL. What is RTL again? Register transfer language. Okay. So logical RTL basically explain the ISA, but physical RTL explain what happened in each cycle. You would see that the physical RTL also include things that we call intermediate registers. Okay? Intermediate register. And the logical RTL didn't say anything about intermediate registers. Yes, please. Oh, both. Well, you happen to know that most people with color blind, they have trouble with red. You know that, right? No. คนที่ตาบอดสีมันจะตาบอดสีแดงเคยทราบไหมไม่ทราบเหรอนั่นคือเหตุที่ Facebook ใช้สีน้ำเงินเพราะมาร์คซักเคอร์เบิร์กตาบอดสีแดง Okay. Now imagine what will happen for the other instructions. We have to do basically the same thing, right? Go from logical RTL to physical RTL. The ORI and ORUI are basically the same thing, right? The difference is just the padding. Otherwise, they're pretty much the same data path. Still remember how the data path worked from previous week, right? From last week. Okay. Move on. Add. Now you see the difference? Add. By the way, if I ask you how many cycles do we need for add instruction, can you answer me? 4. Right? That's what happened. 4 cycles. Okay, let's try this one. Load. So first cycle, we got the IR. Second cycle, we got the operand. Third cycle, we got the address. Fourth cycle, we read from the memory. Last cycle, we write back. So this would take 5 cycles. So now we have all 4 cycles, add 4 cycles, load 5 cycles, and store 4 cycles. Okay. Branch, well, this is a little tricky. We can actually do branch within just 3 cycles if you design the data path properly. Right? Jump, you can also do 3 cycles. Okay, put them all together. This is how our new data path gonna look like. All right. Any questions so far? Or you want me to explain which part in specific details? Okay. Uh-huh. A little bit about this design. Since we do not use both memory at the same time, so it can be same memory. right? It's like first cycle, we use memory for instructions. Fourth cycle, we use memory for data. Since we do not use them at the same time, so it's basically the same memory. Similar things, if you understand how circuit work. Third cycle, we use the ALU for logic operations. Another cycle, we can also use the ALU as adder for the PC. So actually, we can reuse the component because now we overlap time and share some component possible. Okay. We can combine this and combine this. Okay. Overlap the time that we use. All right. Now back to our idea from last week. Once we got the data path, now what? What next? Get the control signal and make the control unit. Okay. So where is the control signal? Here, here. This one. What else? This one, this one, this one. Okay. Then again, do the truth table. But now it's multiple cycle. So we have to explain it with state machine. Okay. Question again. You know what this is? What did you learn from logic, from circuit class? How about this? Ever heard of this word? ASM chart. Anything familiar? No, not at all. No? Okay, no. Okay, let me try to explain this a little bit. Okay. I'm not sure whether you can understand it or not, but again, you should have some background from another class. Okay. The idea is like this. Each circle we call a state. Basically, one state means one clock. So this is one clock. Next clock, you're gonna move to this state because the arrow says so. Okay. And depending on some conditions, next state can be one of them. So it's like you fetch the first instruction in. you decode the instruction. Now, for different kind of instruction, you may go to different state like that. You can use multiplexer or decoder or some kind of circuit logic to go to the next state. Okay, and if it's only one arrow, that means the next clock gonna go to this state. So you would see that some instruction we use only what? 3 states, 1, 2, 3, and then you move back. Some instruction you use 1, 2, 3, 4, and then you go back. Some instruction you use 1, 2, 3, 4, 5. Okay, see the difference? There's one way to explain the cycles, the clock. We call it finite state machine. Okay. Finite state machine. And actually everything about computer and digital world, it's just finite state machine. So now we want to explain the state. One tools to use is finite state machine. There are several tools, and one is ASM chart, but okay, you don't know in any way, it doesn't matter. And then you make table, like, oh, fetch, basically one line for each state, like fetch. What did you do? So this is fetch signal that you have to do in this state. Then what is the next state? So basically this table, the control signal, explain the state machine here. Okay, see the difference? When last week we talked about single cycle processor, we say a table is enough. But now we say, oh, our processor got several cycles. So we use state machine together with a table. But table gonna have something special. We got a new column that we call next state function. Where to go next? Like that. Okay, and in reality, you have to make circuit for this, make our circuit for this. Okay. And I'm not sure whether this would make sense for you. But okay, let's try. Well, since you do not have background in circuit, I mean logic circuit. So there is another way to implement this. We call it microprogram, meaning we try to implement the state machine using small program. We call it microprogram. Okay, let's try. Let's try. Again, let me know if you think it's too difficult, okay? But let's try first. Let's try first. This is how it works. Microprogram got something special we call micro PC, a very small register inside it. And we have control sequence up here, which will make the data part control signal. Okay. But you will understand it better when I show the real examples. Okay. This is the model first. We use micro PC to point to this LUM. Sorry, LUM is like here. So point to this, or this also another LUM. Okay. And it would make sequence. Okay, this is how it works. Let's see the real things here. So it's like this. When you have instruction outside, you fetch in, it's gonna convert into bunch of small micro sequence that basically one sequence for one clock cycle, like that. So sometimes people call this ISA, they call it macro instructions, and they call this sequence micro instruction, just the word anyway. So one macro instruction gonna be translated into several micro instructions inside the processor. Right? And we have to map the ROM by converting state machine to it. So for the micro PC, this is the micro PC. You have three operations to it. Zero means reset, increment +1, and load means load wherever you want to go. And let's try to map these three to our state machine back then. We see something like this. For this, we want to jump back to zero. So we basically say reset zero, go back to the beginning. For each line, it's basically increment of +1. Right? Only time that we want to jump to arbitrary state is load L. So this is just +1, +1, +1. Right? Only this that you would use load. And at the end, you just do zero to jump to the beginning. ไหวไหมงง Oh, this is zero, right? +1 means next state gonna be 1. Okay. This is 1, 1, 1, 0. So this is 1, 1, 1, 1. Just +1. Add 1 to this current state. Okay. That's why I said +1. See? +1. Okay. All this Okay. And this is not +1. Sorry. Okay. This is load, meaning you have to load it with something. So it's not +1. I change the color. Okay. Load. So the meaning is our micro PC is basically the state number. Again, if you learn about finite state machine from other class, it's just another way to implement state machine. But you don't know that, so it's a little details for you. Are we good? Or too much information already? Yes, please. Yes, just one state that we will perform the decode. The fetch is the first state. Fetch is the first state. Once fetch, we decode. Decode, depending on the instruction that we get, we may go to these different states. But once we jump to these different states, we just keep going until we finish. Then we zero, meaning go back to fetch again.
So the loading is like pretty high to state because it doesn't change what the computer is doing.
So decode in this sense is just a name of the state. We name our state decode. And in reality, it's going to be a bunch of circuits that do the real decode. Within each state, it will be combinational circuits that try to do the work. All right. Well, since you do not have background in finite state machine, this might be a little confusing for you for the first time. But again, like I told you earlier, if you understand how it works, that's pretty straightforward. It's just one way to represent state machine. And we just use state machine to represent the state in our processor. So if you get confused, that means you do not have background in the state machine. It's just like that. But I understand that, okay? I did not blame you on anything. But to understand how the processor works, you have to make sense of it a little bit. Okay? So in a sense, there are several ways to do it. There are several ways to do it. Uh-huh. So anyway, if you do not understand it, just leave it. Okay, just leave it. Just try to understand that, oh, we use state to represent each cycle. That's enough. Mhm. And we name the state with some number and real name like that. Okay. So anyway, what have we learned so far? We learned that single cycle is bad because single cycle say we have long cycle like this, and every instruction would use this long cycle, right? So that means if this is L, this long cycle is L. If you have 5 instruction, it's gonna be 5 times 1 times L that long, right? When we change to multiple cycle, it means, oh, some instruction may what? 3 cycles. Some instruction may what? 4 cycles. Some instruction may 5. Yeah. So it's gonna be sometime 3, sometime 4, sometime 5, right? So it's average CPI, which would eventually less than 5, right? And the clock is slightly L divided by 5. That means it's like you partition it into 5 clocks, right? It's L over 5. And the same instruction, that means you eventually faster. It's just the math, we can tell it faster. But impact of that to the processor, you have to add intermediate register. Once you add the intermediate register, what we get is that now we have difference between what? The logical RTL and physical RTL. Let me recap this a little bit. Logical, how you as a programmer see the processor work. Physicals, inside the processor, what happened for each cycle. So physical means cycle accurate, what happens inside the processor. Logical just, oh, I don't care how many cycles. If it works, I'm okay. But this is the architecture class, you have to see inside. Okay, and we ignore the exception for the moment, which would make it difficult. Okay, let's ignore it for now. And I got few exercise that would make you understand, or maybe even worse. Okay, but let's try. Okay, this exercise, I asked you, how many cycles would it take to run this piece of code based on our design of multiple cycle processor? Okay, I'll let you do it a little bit. Okay, what do we get? Low, how many cycles? Five. Five. Branch, three. Add, four. Store. Oh. So it's what? Five, three times four times four. Okay, this 10. This is 8, 18, 21. Right? Okay, 21, right? Uh-huh. And each cycle is what? 40. So it's 21 times 40. Nanoseconds. Okay, good. Thanks.
Oh, I see. Like, you get something to style.
Yeah, I think.
So after the
Maybe this is the old one. Okay. Let me quickly switch to this.